In the discussion on rigid body kinematics, we demonstrated that the motion of a rigid body can be interpreted as a composition of translations and rotations. Now we examine how to describe these two types of special motions in coordinate representation. As already seen, we talk about translation if all the points of a rigid body simultaneously move along congruous curves parallel with each other. These curves are arbitrary curves in space, but in the case of linear translation they consist of straight line segments. Linear translation is an important special case since it is often used to study the relations between different frames of references. The distance and the direction of a translation are determined by the length and the direction of the translation vector. If an arbitrary point P of a rigid body is described by the position vector r with respect to some reference point O, then the position vector r' of the point P after the translation of the body is given by the vector sum of the position vector r and the translation vector delta r. In order to give the coordinate representation of translation, we can attach the origin of a Cartesian coordinate system to the reference point O and describe the position vectors r and r' with its x, y, and z components. Similarly, the Cartesian components of the translation vector can be written as delta x, delta y, and delta z. These coordinates represent the three translation degrees of freedom of rigid bodies translated in space, and we can consider translation as a point transformation of three parameters. Then the vector equation of translation represented in Cartesian coordinates states that the components x', y', and z' describing the position of the point P after translation are equal to the coordinates x, y, and z of the vector are describing its original position, plus the coordinates delta x, delta y, and delta z of the translation vector. The components of the position vector r' are simply the sums of the components of the position vector r and the translation vector delta r. By choosing the orientation of the coordinate system such that one of the coordinate axes points in the direction of the linear translation of the body, we can simplify the coordinate representation of the translation. For example, if the z-axis points in the direction of the translation vector delta r, then the only non-zero component of delta r is its z-coordinate delta z. As a result, the first two Cartesian components of the position vector of point P after translation do not change, and its z component is given by z plus delta z. Obviously, it does not mean that we reduce the degrees of freedom of linear translation to 1, since the special choice of the orientation of the coordinate axes with the reduced number of parameter or parameters gives the complete data for the 3 degrees of freedom of the point transformation. However, this simplification still makes Cartesian coordinates very useful in the quantitative description of linear translations. Curvilinear coordinate systems are less convenient to be adapted to the linear translation of rigid bodies. We can still use a cylindrical coordinate system to simplify the representation of translation by directing its z-axis parallel with the translation vector, and reduce the non-zero parameters of the translation to the z-coordinate. There is no such option for spherical polar coordinates. Even if we translate a rigid body in radial direction, the polar and azimuthal angles of any point of the body still change after the translation. Now we derive the coordinate representation for the rotation of rigid bodies. Starting with the planar rotation of the points of a rigid body, we determine the coordinate representation of the rotation of a point in a Cartesian coordinate plane. Let us attach a Cartesian coordinate system to a frame of reference such that the origin of the coordinate system is at the reference point O of the frame, and a given point P of a rigid body is on the positive x-axis. That is, the position vector r of the point P points in the direction of the positive x-axis. If we rotate the point P about the origin through the angle alpha in the xy plane, then we obtain the point P' described by the position vector r'. The Cartesian coordinates of the point P are given by x and y, whereas the coordinates of the point P' are denoted by x' and y'. Since we rotated the position vector r about the origin O, its length is equal to the length of the position vector r'. As a result, we can write the x-coordinate of the point P' as the magnitude r times cosine alpha, which is equal to x times cosine alpha. Similarly, the y-coordinate of the point P' is given by the magnitude r times sine alpha, or x times sine alpha. Now we can consider a more general case, where the point P is not on the x-axis and the angle alpha measured between its position vector r and the positive x-axis is arbitrary. Here the coordinates x and y of the point P are given by the length of the position vector r times cosine alpha, and r times sine alpha respectively. Now we rotate the point P about the origin O through the angle beta in the xy plane, and obtain the point P' with the coordinates x' and y' given by r times the cosine of the sum of the angles alpha and beta, and r times the sine of the sum of alpha and beta respectively. By applying trigonometric relations for the cosine and the sine of the sum of the angles, we can write the coordinates of the point P' as follows. The coordinate x' can be written as r times the difference between cosine alpha times cosine beta and sine alpha times sine beta. If we expand the brackets in the right-hand side of the equation, then we obtain r times cosine alpha times cosine beta, minus r times sine alpha times sine beta. By substituting the coordinates x and y of the point P into the products, we can write the coordinate x' as x times cosine beta minus y times sine beta. Similarly, the coordinate y' can be written as r times the sum of sine alpha times cosine beta and cosine alpha times sine beta. The right-hand side is equal to r times sine alpha times cosine beta, plus r times cosine alpha times sine beta, which gives y times cosine beta plus x times sine beta. As a result, the coordinates x' and y' of the point P' rotated about the origin through the angle beta in the xy plane are given by the following equations. X' is equal to the x-coordinate of the point in its initial position times the cosine of the rotation angle beta, minus the y-coordinate of the point in its initial position times sine beta. Y' is given by the y-coordinate times the cosine of the angle beta, plus the x-coordinate times the sine of the angle beta. We can also write these two equations in vector notation, where the column vector in the left-hand side describes the coordinates of the point P', and the right-hand side is the product of a 2 times 2 matrix and the column vector describing the coordinates of the point P. Here the matrix with the elements cosine beta, minus sine beta and cosine beta is the coordinate representation of the rotation of a point about the origin O through the angle beta in the xy plane, which is also called the rotation matrix of the planar rotation. We can generalize planar rotations about the origin of a Cartesian coordinate system to spatial rotations about one of the coordinate axes, and determine their coordinate representation by using the one derived for planar rotations. The straightforward generalization of the rotation of a point in the xy plane is the rotation of the point P about the z-axis in a plane parallel with the xy plane. The distance of the plane of rotation from the xy plane is given by the coordinate z at the point O, where the z-axis passes through the plane of rotation. The coordinates of the position vector are pointing from the point O to the point P are the coordinates x, y and z, where the coordinates of the position vector are prime pointing from the point O to the point P' are described by the primed Cartesian coordinates. Here the angle alpha is measured between the xz plane and the position vector r, and beta is the angle of rotation measured between the position vectors r and r'. In the case of planar rotation, we obtain the x' and y' coordinates of the point P by multiplying the column vector of the x and y coordinates of the point P with the rotation matrix. We can extend this two-dimensional equation to a three-dimensional one if we take into account the fact that the z-coordinate of the point P is invariant under the rotation, that is z' is equal to z. As a result, we can write the coordinates of the point P' given by the column vector of the coordinates x', y' and z' as the product of a 3 times 3 matrix and the column vector of the coordinates x, y and z. The matrix of the planar rotation in the xy plane forms the first 2 rows and columns of the matrix of the spatial rotation, whereas the third row and the third column of the matrix are constructed from zeros and the number 1 such that the multiplication of the in the right-hand side gives the primed coordinates where z' is equal to z. Then the 3 times 3 matrix in the right-hand side of the vector equation is called the rotation matrix of the rotation of any point about the z-axis through the angle beta. We will follow the same procedure to derive the rotation matrices for the rotations about the x and y axes of the Cartesian coordinate system. For the rotations about the x-axis we can choose any plane of rotation parallel with the yz plane. Here the plane of rotation passes through the x-axis at the point O, and the position vectors r and r' pointing from the point O to the points P and P' are parallel with the yz plane. The coordinates x', y' and z' of the point P' are expressed as the product of a 3 times 3 matrix and the column vector of the coordinates x, y and z. Now the matrix of the planar rotation in the yz plane forms the second and the third rows and columns of the matrix, where the first row and column are constructed such that the multiplication of the matrix and the column vector in the left-hand side gives the primed coordinates where x' is equal to x. 10. This matrix is the rotation matrix of the rotation of a point about the x-axis through the angle beta. Similarly, we can determine the coordinate representation of the rotations about the y-axis by choosing any plane of rotation parallel with the zx plane. In this case the plane of rotation passes through the y-axis at the point O, and the position vectors r and r' pointing from the point O to the points P and P' are parallel with the zx plane. The column vector of the coordinates of point P' are given by the product of a 3 times 3 matrix and the column vector of the coordinates of the point P. Here the second row and column of the matrix vanish except the diagonal element, which is 1. The rest of the elements in the corners of the matrix are constructed from the matrix of the planar rotation in the zx plane through the angle beta. Since the direction of the rotation is the opposite to the one for the first two cases, the rotation angle beta has a negative sign which changes the sign of sine beta since it is an odd function. The resulting 3 times 3 matrix is the rotation matrix of the rotation about the y-axis through the angle beta. Then we have 3 matrices providing the coordinate representation of spatial rotations about the 3 Cartesian coordinate axes. The matrix R x hat alpha represents the rotation of an arbitrary point about the x-axis through the angle alpha, where the bold-faced letter x with hat denotes the unit vector pointing from the origin in the direction of the x-axis. Similarly, the matrices RY hat alpha and RZ hat alpha represent the rotations about the y and z axis respectively, where y hat and z hat are the unit vectors pointing in the direction of the y and z axes and alpha is the angle of the rotations. In the general case, rigid bodies can be rotated about an arbitrary axis in the space, and the properties of the rotation matrices for general rotations can also be determined without selecting any specific direction for the rotation axis. The figure shows a rigid body rotating about the axis specified by the unit vector n through the angle alpha. The orientation of the vector n is chosen such that it forms a right-handed system with the positive direction of the rotation. As a result, the point P described by the position vector are pointing from a reference point O on the rotation axis to the point P is rotated to the point P' described by the position vector R' pointing from the point O to the point P'. Then the position vector R' can be written as the product of the rotation matrix Rn alpha representing the rotation and the position vector R. Here the 3 times 3 matrix R is the rotation matrix for rotations about the unit vector n through the angle alpha, where the elements of the matrix depend on the direction of the vector n and the rotation angle alpha. Although the axis and the angle of rotation are arbitrary, rotation matrices have some general properties which we present here. The first property immediately follows from the fact that the distance between any 2 points of a rigid body is constant during its motion. This distance is therefore invariant under the rotation of the body, and the length of the position vector r with the tail on the axis does not change when the body is rotating about the axis. As a result, the magnitude of the position vector r' of the point after the rotation is equal to the magnitude of the initial position vector r. In other words, the scalar product of the vector r' with itself is equal to the scalar product of the vector r with itself. Here the position vector r' can be written as the product of the rotation matrix Rn alpha and the position vector r. Since the scalar product of two vectors in coordinate representation is actually the product of a column vector and a row vector, the column vector of the left-hand side factor in the dot product can be written as the transpose of the product of the matrix R and the position vector r. The transpose of the product is equal to the vector r times the transpose of the matrix R. If we compare the two sides of the vector equation, then we conclude that the transpose of the matrix R times the matrix R must be equal to the unit matrix I. Two important results follow from this equation. The first one tells us that the transpose of the rotation matrix R is equal to its inverse. The second result is based on the fact that the determinants of a matrix and its transpose are equal, and tells us that the square of the determinant of the matrix R is equal to 1. Such matrices are called orthogonal matrices, that is the rotation matrix of a general rotation is an orthogonal matrix. Other properties of the rotation matrix also follow from geometric considerations. We can rotate a rigid body about a fixed axis of rotation given by the unit vector n in 2 steps. First we rotate the body through the angle α1, and then through the angle α2, which is equivalent to the rotation of the body in 1 step through a rotation angle given by the sum of the angles α1 and α2. The matrix representation of this property is expressed by the equation stating that the product of the rotation matrices Rn α1 and Rn α2 is equal to the rotation matrix Rn α1 plus α2. Although the matrix multiplication is not commutative, the order of the factors in the product does not matter for rotations about the same axis. Another important property is the periodicity of the rotation angle. It is obvious that a rigid body does not change its orientation if we rotate it through 360 degrees, that is, we have an identity transformation. In the general case, we describe the periodicity of rotations by stating that the rotation matrix Rn alpha plus 2 pi times k is equal to the rotation matrix Rn alpha, where k is an arbitrary integer number. It is also clear that the inverse rotation of a rigid body about a given axis through a given angle is equivalent to its counterclockwise rotation about the same axis through the same angle. In a mathematical representation, the inverse of the rotation matrix Rn alpha is equal to the rotation matrix Rn minus alpha. Due to the convention used for the orientation of the unit vector n, we can write the right-hand side as the rotation matrix R minus n alpha. It follows from the periodicity of rotations and the properties of inverse rotations that the rotation matrix R of the rotation about the axis given by the unit vector n through the angle 2 pi minus alpha is equal to the rotation matrix Rn minus alpha. The right-hand side is equal to the rotation matrix R minus n alpha, that is, any spatial rotation of a rigid body can also be described by a counterclockwise rotation through the original rotation angle alpha plus 180 degrees. We already saw that the spatial rotation of rigid bodies can be described by the Euler angles. The axis and the angle of rotation determines the rotation matrix, and the Euler angles of the rotations can be computed from the elements of this matrix. Conversely, general rotations can be constructed from Euler rotations, that is, the rotation matrices of general rotations can be expressed in the terms of the Euler angles. When we define the Euler angles by introducing the three Euler rotations of a Cartesian coordinate system, we use the following convention. First, we rotate the coordinate system counterclockwise about its z-axis through the angle psi. Then we rotate the coordinate system counterclockwise about its x-axis through the angle theta. In the last step, we rotate the coordinate system counterclockwise about its z-prime axis through the angle phi such that the axes x and y are brought into the x-prime and y-prime axes. If we attach a rigid body to the coordinate system and rotate them together and describe the position of the points of the body in the original coordinate system, then the product of the rotation matrix and the position vector of any point of the body gives the new position of the point after rotation. Since the Euler rotation is the composition of the three rotations of the Cartesian coordinate axes, the rotation matrix R expressed in the terms of the Euler angles psi, theta, and phi can be written as the product of the rotation matrices R z hat prime phi, R x hat theta, and R z hat psi. In order to compute the product of the three matrices, we start with the multiplication of the second and the third matrices in the product. We write the elements of the third matrix, that is the matrix R z hat psi, in a table, and the elements of the second matrix, that is the matrix R x hat, in another table such that their mutual positions determine the result of their multiplication. This arrangement facilitates the computation of any element in a given row and a given column of the product matrix obtained from the dot product of the corresponding row of the second matrix and the corresponding column of the third matrix. The product of the first row of the second matrix and the first column of the third matrix and gives the top left element of the resulting matrix, which is equal to cosine psi. The product of the first row of the second matrix and the second column of the third matrix is equal to minus sine psi for the top middle element of the resulting matrix. The product of the first row of the second matrix and the third column of the third matrix gives the vanishing top right element of the resulting matrix. Similarly, the product of the second row of the second matrix and the first column of the third matrix gives the middle left element of the resulting matrix, which is equal to cosine theta times sine psi. The product of the second row of the second matrix and the second column of the third matrix is equal to cosine theta times cosine psi for the element in the center of the resulting matrix. The product of the second row of the second matrix and the third column of the third matrix gives minus sine theta, the middle right element of the resulting matrix. The product of the last row of the second matrix and the first column of the third matrix gives the bottom left element of the resulting matrix, which is equal to sine theta times sine psi. The product of the last row of the second matrix and the second column of the third matrix is equal to sine theta times cosine psi for the bottom middle element of the resulting matrix. The product of the last row of the second matrix and the last column of the third matrix gives cosine theta, which is the bottom right element of the resulting matrix. If we multiply this result with the first matrix in the product, that is with the matrix R z hat prime phi, then we obtain the general rotation matrix in the terms of the Euler angles. The product of the first row of the first matrix and the first column of the resultant matrix gives the top left element of the general rotation matrix. The first row of the first matrix multiplied by the second column of the resultant matrix gives the top middle element of the rotation matrix. The product of the first row of the first matrix and the last column of the resultant matrix is equal to the top right element of the rotation matrix. Similarly, the product of the second row of the first matrix and the first column of the resultant matrix gives the middle left element of the general rotation matrix. The second row of the first matrix multiplied by the second column of the resultant matrix gives the central element of the rotation matrix. The product of the second row of the first matrix and the last column of the resultant matrix is equal to the middle right element of the rotation matrix. The product of the last row of the first matrix and the first column of the resultant matrix gives the bottom left element of the general rotation matrix. The last row of the first matrix multiplied by the second column of the resultant matrix gives the bottom middle element of the rotation matrix. Finally, the product of the last row of the first matrix and the last column of the resultant matrix is equal to the bottom right element of the rotation matrix. As a result, we have obtained the rotation matrix of general rotations in terms of the Euler angles psi, theta and phi. Although this matrix seems to be somewhat complicated, its inverse, that is the matrix of the inverse Euler rotations, is simply given by the transpose of this matrix. The rotation matrix can also be used to determine the Euler angles for the general rotation if its rotation matrix is already given. For a rotation axis described by the unit vector n and the rotation angle alpha, we can compute the elements r sub ij of the rotation matrix capital R n alpha as the functions of the Cartesian components of the unit vector and the angle alpha, where the indices I and j run from 1 to 3. Since this general form of the rotation matrix is equal to the rotation matrix expressed in terms of the Euler angles, the individual elements of the two matrices are the same. Then we can express the Euler angles as the functions of the elements r sub ij. For example, by comparing the elements in the bottom right corners of the matrices, we can express the Euler angle theta as the arc cosine of the element r sub 3. We use the index 1 for the angle since it is determined up to a shift of 180 degrees, that is pi plus theta 1 is also a solution and theta 2 can be written as pi plus the arc cosine of the element r sub 3. If theta 1 and theta 2 are given, we can determine the other two Euler angles as well. After dividing the elements r sub 3 and r sub 3 by sine theta 1, we take their ratio and express the angle psi 1 as the arctangent of the ratio of r sub 3 divided by sine theta 1 to r sub 3 divided by sine theta 1. We have the same expression for psi 2, where the matrix elements are divided by sine theta 2. Similarly, we can divide the elements r sub 1 and r sub 2 by sine theta 1, and express the angle phi 1 as minus the arctangent of the ratio of r sub 1 divided by sine theta 1 to r sub 2 divided by sine theta 1. We have the same expression for phi 2, where the matrix elements are divided by sine theta 2. As a result, we have two representations of the general rotation matrix expressed either in the terms of the unit vector n determining the rotation axis and the rotation angle alpha, or in the terms of the Euler angles psi, theta and phi. We note that there are several conventions for the definition of the Euler angles with different notations for the angles and different sequences of the Euler rotations for the coordinate axes. If we apply a different convention, then the rotation matrix seen in the top will have a different form and the expressions obtained for the Euler angles will be different as well. However, the procedure for their derivation presented here is still the same. As already seen above, we can simplify the description of the translation of rigid bodies in space by using a Cartesian coordinate system with one of its axes pointing in the direction of the translation. In the case of the rotating rigid bodies, we can also adapt coordinate systems to the trajectories of the motion, and use curvilinear coordinates in the description of the points of rotating bodies. We can study the motion of a rotating rigid body in a cylindrical coordinate system if the body rotates about a fixed axis. Any two fixed points of a rigid body determine an axis about which the body can rotate, for example a bicycle will attach to its axle. In other cases rigid bodies can rotate over some constrained surface like a toy train moving on a circular track, or a ball bearing where one of the races is fixed while the other one is allowed to rotate by the separated balls between the races. The description of such a motion becomes very simple in a cylindrical coordinate system with its origin on the axis while its z-axis points in the direction of rotation axis of the body. Any point P of the rotating body can be described by the position vector r with the coordinates ρ, phi and z. Since the coordinate ρ is the distance of the point from the axis of the coordinate system that is the axis of rotation, it is invariant under the rotation of the body. Similarly, the points of the body do not move along the axis z, and the z-coordinate of their rotating position vector remains constant. If r' denotes the position vector of the point P' after rotation, we can write the vector equation stating that the components ρ', phi' and z' of the vector r' are equal to ρ, phi plus delta phi and z respectively. Here delta phi gives the change in the azimuthal angle of the rotating point. As a result, the azimuthal angle completely describes the motion of the rigid body during its rotation, which simplifies the analysis of the problem. A spherical coordinate system can be used to describe rotating motion as well. If we fix only one point of the rigid body, then it can rotate about the fixed point in an arbitrary direction. As a result, all the points of the body can be rotated over the spheres of radii given by the distances of the points from the fixed point, that is from the center of rotation. Typical examples of such a spherical rotation are a spinning top with its tip constrained to a cup with its top end slowly revolving about the tip, and a spherical pendulum swinging on a surface of a sphere. By using a spherical coordinate system with its origin at the center of rotation, we can simplify the description of the motion of the rotating body. The position vector of any point P of the body has the components describing its distance are from the center, the polar angle theta and the azimuthal angle phi. If r prime denotes the position vector of the point after rotation, then we can write the vector equation stating that its primed coordinates are equal to r, theta plus delta theta, and phi plus delta phi respectively. Since the polar and azimuthal angles of the rotating points describe the motion of the rigid body, we only need to study the change in these two coordinates during the rotation. In both cases, the trajectories of the points of the rigid body have a simple description in curvilinear coordinates and no rotation matrix is needed to transform the coordinates of an initial point to the ones of the point after rotation. Although curvilinear coordinate systems adapted to the symmetries of rotation simplify the study of the motion of the rigid bodies, their application are only convenient if the center or the axis of rotation is fixed. Otherwise, it is better to use Cartesian coordinates to describe the motion of a rigid body rotating about an instantaneous center or axis. The application of a Cartesian coordinate system attached to the frame of reference is the most general method for the quantitative description of the rotating motion of rigid bodies without fixed center or axis of rotation, where kinematics is described by the action of rotation matrices on the points of the rotating body. In the context of the coordinate representation of rotations, we need to mention another type of point transformation, and this is reflection. At first sight, reflections of geometric points in space do not seem to have anything to do with the physical motion of rigid bodies, but this geometric transformation has an important role in the classification of rotations. When we talk about the reflection of a rigid body in space, we imagine an arbitrary plane in the vicinity of the body serving as a plane of reflection. The image of the body appears on the opposite side of the plane, and it has the same distance from the plane of reflection as the rigid body. If the images of the points A, B, C and D of the body are denoted by the primed letters, then we can write that the distance d sub AO is equal to the distance d sub A prime O. That is the intersection point O of the section AA prime, and the plane of reflection is the midpoint of the section AA prime. Similar equations can also be given for the points B, C, D and for other arbitrary points of the rigid body with the corresponding points of intersection. We can also see that although the shape of the image remains congruent to the original, it has a reverse orientation, that is, the image does not flip left to right. If the original points A and B are in the front, then the reflected points A' and B' are in the front as well. We can obtain the coordinate representation of the reflection if we attach a Cartesian coordinate system to the plane of reflection such that one of its coordinate plane, for example the YZ plane, is in the plane of reflection. If any point of the rigid body has the x, y and z coordinates in this coordinate system and its image has the primed Cartesian coordinates, then the distance equation of the original points and their images has the coordinate representation stating that the coordinates x', y' and z' of the image are equal to -x, y and z, respectively. The right-hand side can be written as the product of a 3x3 diagonal matrix and the column vector x, y and z, where the non-zero component in the diagonal are -1, 1 and 1. This matrix is the coordinate representation of the reflection across the YZ coordinate plane, and it is denoted by p sub x hat, where the unit vector x hat is the normal to the plane of reflection. We can derive the reflection matrices for the other two coordinate planes as well, where all the Cartesian reflection matrices p sub x hat, p sub y hat and p sub z hat are diagonal matrices, with the diagonals 1, -1, 1 for p sub y hat, and 1, 1, -1 for p sub z hat. If the normal to the plane of reflection has an arbitrary direction, we can rotate the plane together with the body into any of the coordinate plane, perform the reflection of the body and apply an inverse rotation on the image. We have already shown that rotations can be represented by orthogonal matrices, which are denoted by the capital letter O. In other words, the square of the determinant of a general rotation matrix R is equal to 1. As a result, the determinant is equal to either +1 or -1. If the determinant of a matrix is equal to 1, we call it as a special orthogonal matrix denoted by the capital letters SO, and such matrices represent the proper rotations of rigid bodies in space. If the determinant of a matrix is equal to -1, then it can be written as the product of a special orthogonal matrix and a reflection matrix. In other words, it is a composition of a proper rotation and a reflection in space. Such operations are also known as improper rotations. Then we conclude that a general rotation about an axis given by the unit vector n through the angle alpha is represented by special orthogonal matrices, which can have different elements in different coordinate systems but their determinant is always equal to 1. Improper rotations are represented by the product of a special orthogonal matrix are depending on a given unit vector n and angle alpha and a reflection matrix Pm, where m is the unit normal to a plane of reflection.